This is Sarah. She built a successful online store, but her login code hasn't been touched in 2 years. Then there's Dan. He doesn't need Sarah's password. He doesn't need to break into the server. He just needs to find one mistake in the login query. Because when user input is placed directly into a database query, the login form can become more than a login form. It can become a way into the database. That's SQL injection. And today, we're going to watch how an attacker finds it and what that single mistake can expose. First, Dan needs to confirm the login page is actually reachable. 3 packets out, 3 back. The target's alive. Next, Dan wants to see what's actually running on the server before touching anything. Port 80's open, Apache, with PHP behind it. That lines up with what Dan expected from a small, custom-built store. Now he opens the login page directly in a browser to see the form itself, then grabs the exact request it sends. At first, it looks like a completely standard login form, just an email, a password, and a sign-in button. Nothing unusual on the surface. But the interesting part isn't what the form looks like. It's what happens to that input after you hit sign in. Before bringing in any automated tool, Dan does what a careful tester always does first, a manual sanity check. First, Dan sends a completely normal login attempt with a test email and password. Nothing unusual happens, the server processes the request and redirects back to the application. Now Dan changes just one thing, a single character with special meaning in SQL syntax. And the response changes. Instead of simply rejecting the login, the server throws back a SQLite database error. That single quote broke the query and exposed an error that should never be visible to a normal user. That's a strong clue that the application's SQL query is handling user input unsafely. But a clue isn't proof. So now Dan brings in SQLMap to test it systematically. SQLMap takes the same request Dan just tested by hand. Instead of trying one payload at a time, it systematically tests the login parameters against multiple SQL injection techniques. And within a few seconds, SQLMap finds the actual injection point. The email parameter isn't injectable, but the password parameter is. SQLMap identifies a union-based injection with 4 columns and then confirms that the backend database is SQLite. So this isn't a guess anymore. SQLMap has confirmed that Dan can manipulate the SQL query through the password field. Now Dan wants to know what's actually inside the database. Since the backend is SQLite, there's no need to search for a MySQL-style database name. Instead, he asks SQLMap to enumerate the tables. The table names come back, and one immediately catches his attention: admin_users. That's where the administrative accounts are stored. Tables appear: customers, orders, admin users, sessions. Dan goes straight for the one that matters most. And there it is. SQLMap has dumped the admin users table. We can see the admin username, the password hash, and then something even more interesting. SQLMap has already recognized the hash and recovered the original password admin123. So Dan now has an actual admin credential, not just a hash. But what if SQLMap doesn't recover the original password automatically? In a real assessment, we shouldn't assume that a password hash is useless just because the plain text isn't immediately visible. At this point, we have something much more valuable than a username alone. We have the administrator's password hash. So let's analyze the hash first. The first step is identifying what kind of hash we're dealing with. I'm using hash ID to analyze the value. Notice something important here. The tool reports several possible algorithms, including MD5. That's because a hash format alone doesn't always prove the exact algorithm. But in this controlled lab, we already know the application uses an unsalted MD5 password hash. And that matters because MD5 is extremely fast to calculate, exactly the opposite of what we want for password storage. Now I'll save the hash into a file. This gives Hashcat a clean input to work with. Again, we're not attacking another system here. This is the administrator hash we just extracted from our isolated CartlyShop laboratory environment. Now comes the password recovery step. I'm using Hashcat with mode 0, which corresponds to MD5 and a dictionary attack using the RockYou word list. Instead of randomly guessing passwords, Hashcat takes each candidate from the word list, calculates its MD5 hash, and compares the result with our target hash. If the hashes match, we've recovered the original password, and there it is. The hash has been cracked. The value on the left is the original hash, and the value on the right is the recovered password, admin123. This is exactly why password hashing isn't just about hiding the password. The hashing algorithm and the way it is configured determine how difficult that password is to recover. And there's an important security lesson here. The problem isn't simply that the password was short. The bigger problem is that the application used a fast, unsalted hashing algorithm. A modern password storage system should use a deliberately slow password hashing function, such as argon2id or bcrypt, with a unique salt for every password. That makes large-scale offline guessing dramatically more expensive. Now we have a username and a recovered password. Let's verify them against the lab application. The server returns a 302 redirect to /admin and sets a session cookie. That's our confirmation. The credentials worked. So let's recap. A single quote exposed the SQL injection. SQLMap confirmed the vulnerable parameter and identified SQLite. We extracted the admin users table, recovered the password hash, and cracked it to admin123. One vulnerable query led to database access, credential exposure, and finally, an authenticated admin session. One query, one weak password, one complete attack chain. The fix is well established. First, use parameterized queries or prepared statements. User input should always be treated as data, never as SQL code. Second, follow the principle of least privilege. Your application shouldn't have permission to access every table in the database. Third, never store passwords using fast, unsalted hashes like MD5. Use modern algorithms such as argon2 or bcrypt with proper salts. And finally, test your own applications in a safe lab environment. Tools like SQLMap can help you find these vulnerabilities before someone else does. Because this entire attack chain started with something incredibly simple, one vulnerable input field. One SQL injection led to database access, credential exposure, password recovery, and an authenticated admin session. That's the real lesson. Don't just protect the login page. Protect everything behind it. If you found this useful, hit like, subscribe, and I'll see you in the next one.